Look at your hands. Look at the room around you. Everything you have ever touched, seen, or interacted with exists strictly across three spatial axes: up and down, left and right, forward and backward. For hundreds of millions of years, biological evolution has hardwired your visual cortex to translate light bouncing off matter into this three-dimensional framework. But what if your eyes have been filtering out the true geometry of the cosmos all along? What if there is an entire extra spatial direction right next to you that you physically cannot point toward? If your perceptual apparatus suddenly gained the ability to process a fourth spatial dimension, reality as you know it would instantly collapse and reconstruct itself before your eyes. You would no longer see the surface of things. You would see through solid concrete, peer into the locked steel chambers of bank vaults without opening their doors, and observe the inner mechanics of living organisms, including the pumping ventricles of a human heart, with absolute clarity. Solid boundaries would vanish, and the universe would unfold its deepest geometric architecture right into your field of view. Today, we are going to explore what would happen if you could see the fourth dimension. Before we dive deep into the mind-bending physics and geometry of higher dimensional space, feel free to like this video and subscribe to the channel if you enjoy deep dives into theoretical science. Also, leave a comment below letting us know where in the world and what time you are watching this from. Now, let us begin our journey beyond the limits of three-dimensional space. To truly grasp what it means to look into the fourth dimension, we have to strip away our biological intuition and rebuild our understanding of space from the ground up. In everyday life, human intuition is deeply tied to the tangible world. We define space through physical boundaries, physical directions, and physical coordinates. However, geometry does not care about human biological limitations. In mathematics, a spatial dimension is simply an axis of movement, a degree of freedom along which a point can move perpendicular to every other available axis. Let us begin at the absolute baseline of spatial geometry, zero dimensions. A zero-dimensional space is an infinitesimal point. It has no length, no width, and no height. A point possesses 0 degrees of freedom. A theoretical entity existing purely within 0 dimensions cannot travel forward, backward, left, right, up, or down. It simply occupies a discrete coordinate in existence. It has no internal volume, no external surface, and no structural perspective. Now, take that zero-dimensional point and drag it across an empty void along a single straight path. By extending this point continuously through space, you generate a line segment. You have just constructed the first dimension. A one-dimensional universe possesses a single axis of freedom, which we can call the x-axis. An inhabitant of this one-dimensional realm can only move forward or backward along this linear trajectory. If two one-dimensional entities encounter one another on this line, they cannot step around each other. Because there is no lateral space, no left or right, their collision is absolute. The front of one entity forever blocks the path of the other. Their entire universe is defined purely by length. Next, take that entire one-dimensional line segment and pull it outward at a 90-degree angle to its original direction. By extending every point along that line through a new direction, you sweep out a flat geometric surface known as a square. You have created the second dimension. This introduces a second axis of movement, the y-axis, which is perfectly perpendicular to the x-axis. A two-dimensional universe has both length and width, yet it possesses absolutely 0 thickness or height. Entities living within this planar geometry can navigate forward, backward, left and right. They can walk around one another. However, the concept of above and below remains completely alien to them. If a two-dimensional creature is trapped inside a closed perimeter, such as a square drawn on a sheet of paper, it is thoroughly imprisoned. To escape, it would need to cross the boundary line, because it has no access to an upward direction that would allow it to step over the drawn perimeter. Now, repeat this precise geometric operation once more. Take that two-dimensional square and pull it outward into a direction that is perpendicular to both the x-axis and the y-axis simultaneously. By pulling it vertically upward, you sweep out a solid three-dimensional cube. This introduces the z-axis, the familiar axis of height and depth. In our three-dimensional reality, we possess three mutually perpendicular directions: length, width, and height. In this three-dimensional framework, our hypothetical prisoner trapped inside the drawn square on the paper can simply reach down from above, pick up the trapped object along the z-axis, move it through the air, and place it back down outside the boundary. To a two-dimensional observer watching only the plane of the paper, the object would appear to dematerialize into nothingness and rematerialize elsewhere, in complete defiance of their understood physical laws. This brings us to the ultimate geometric leap. What happens when you apply this exact same recursive rule one more time? Take a three-dimensional solid cube and drag it into a new direction that is simultaneously perpendicular to the x-axis, the y-axis, and the z-axis. To human sensory perception, this seems physically impossible. Look at any corner of the room you are sitting in right now. You will see three edges meeting at a single vertex, forming three distinct 90-degree angles. The edge along the floor stretching left to right, the edge stretching forward into the room, and the vertical edge running up to the ceiling. If you try to add a fourth physical rod to that same vertex, such that it forms a 90-degree angle with all three existing edges at the same time, your brain hits a hard perceptual wall. There is simply no room in three-dimensional space to fit a fourth perpendicular axis. Yet in pure geometry, this axis exists. Mathematicians designate this fourth spatial coordinate as the w-axis. By sweeping an entire three-dimensional cube through this fourth perpendicular direction, you construct a four-dimensional spatial analogue of the cube, known in higher dimensional geometry as a tesseract or a four-dimensional hypercube. Just as a two-dimensional square is bounded by four one-dimensional line segments, and a three-dimensional cube is bounded by six two-dimensional square faces, a four-dimensional tesseract is bounded by 8 three-dimensional cubes. It is an object whose exterior walls are not flat squares, but entire solid three-dimensional volumes. Because our human biological hardware is physically confined to 3 dimensions, we cannot look directly at a tesseract in its native environment. However, we can completely understand its nature through dimensional analogy. This conceptual bridge was brilliantly illustrated by the 19th century mathematician and educator Edwin Abbott in his groundbreaking novella Flatland, a romance of many dimensions. Abbott invited readers to imagine a universe called Flatland, a two-dimensional planar world populated by geometric shapes like triangles, squares, and circles sliding smoothly across the surface of an infinite flat tabletop. These flat creatures live their entire lives interacting exclusively within the boundaries of their two-dimensional plane. They have no anatomical mechanism to look up or look down, nor do they even possess words or concepts for those directions. For a flatlander, the universe consists entirely of forward, backward, left, and right. Imagine what happens when a three-dimensional sphere visits Flatland. The sphere descends from above, hovering directly over the planar world. From the sphere's three-dimensional vantage point, it can see the entire layout of Flatland at once. It can see inside every house, look past every closed, locked door, and observe the internal organs of every Flatlander simultaneously, without piercing any skin or breaking any walls. To the sphere, the interior of a closed two-dimensional shape is completely exposed, because the boundary walls only block access within the plane, not from the third dimension above. When the three-dimensional sphere speaks to a Flatland square, its voice appears to emanate from everywhere and nowhere at once, echoing from within the square's own body, because sound waves arrive along an axis the square cannot perceive. The sphere tries to explain the concept of upward, but the square insists that no such direction exists. To prove its physical reality, the three-dimensional sphere decides to pass directly through the plane of Flatland. What does the two-dimensional square actually see? The square does not see a sphere. A three-dimensional sphere cannot fit inside a two-dimensional plane all at once. Instead, the square only perceives a series of two-dimensional cross-sections, slices of the sphere intersecting the plane of Flatland. As the bottom of the sphere first makes contact with the flat surface, the square witnesses a single microscopic point spontaneously appear out of empty space. As the sphere continues to descend, that point rapidly expands into a small circle. As the widest part of the sphere, its equator, passes through the plane, the circle swells to its maximum diameter. Then, as the upper half of the sphere moves through, the circle steadily shrinks, becomes a microscopic point once again, and suddenly vanishes into nothingness. To the Flatland square, this event looks like pure supernatural magic. A solid object materialized out of absolute vacuum, morphed in size and vanished without a trace. Yet from our higher three-dimensional perspective, nothing magical occurred at all. A rigid, invariant three-dimensional object simply passed steadily along an axis that the flat observer could not detect. Now flip this analogy directly onto our own human existence. Imagine a four-dimensional hypersphere drifting slowly through the three-dimensional space of our universe. Because our eyes and retinas can only receive three-dimensional intersections, we would never see the four-dimensional hypersphere in its totality. Instead, we would witness its three-dimensional cross-sections slicing through our space. You would stand in your living room and suddenly watch a solid, perfectly spherical object appear suspended in mid-air from absolute nothingness. It would not drop from the ceiling or enter through a doorway. It would simply phase into physical existence at a specific point in space. As the hypersphere continued its movement along the four-dimensional W-axis, the floating three-dimensional sphere would smoothly expand in volume, growing larger and larger before your eyes. It would reach a maximum size, and then it would begin to shrink, steadily contracting until it reduced to a single point and instantly disappeared. If you tried to reach out and touch it, you would feel a solid, impenetrable three-dimensional mass. Yet you would be touching only an infinitesimal cross-sectional boundary of a far larger four-dimensional structure that extends along a physical direction you cannot point toward. By understanding the geometry of spatial dimensions and the profound lesson of the Flatland paradox, we realize that our conventional sensory world is not the ultimate limit of physical reality. It is merely a single three-dimensional slice of a potentially grander, multidimensional geometric universe. When discussing the fourth dimension, one of the most common points of scientific confusion arises from the intersection between modern physics and pure spatial geometry. If you ask a theoretical physicist about the fourth dimension, they will frequently refer to the framework established by Albert Einstein in his special and general theories of relativity. In relativistic physics, the fourth dimension is treated as time, woven together with three spatial coordinates into a unified four-dimensional fabric known as spacetime. However, if you ask a pure mathematician or a string theorist, they are often describing a fourth spatial dimension, an entirely separate physical direction perpendicular to length, width, and height. To truly understand what it would mean to perceive higher dimensions, we must rigorously untangle these two distinct concepts and analyze how reality shifts depending on whether the fourth dimension is temporal or purely spatial. Let us begin with Einstein and the revolutionary contributions of the mathematician Hermann Minkowski. Prior to the 20th century, classical Newtonian physics treated space and time as completely independent entities. Space was viewed as a static, unchanging three-dimensional stage upon which the events of the universe took place, while time was considered an absolute, universal clock ticking steadily and uniformly for all observers throughout the cosmos, regardless of their motion or gravitational surroundings. Einstein shattered this classical foundation. He demonstrated that the speed of light in a vacuum is an absolute, invariant physical constant across all inertial frames of reference. Because light always travels at the exact same velocity regardless of how fast an observer is moving, space and time cannot remain absolute. Instead, space must contract and time must dilate depending on the relative velocity of the observer and the strength of the surrounding gravitational field. In 1908, Minkowski formalized this insight by demonstrating that space and time are fundamentally inseparable. He famously proclaimed that, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. In Minkowski spacetime, any physical event requires four coordinates to specify its exact location in the universe: three spatial coordinates along the x, y, and z axes, and one temporal coordinate along the time axis. However, in standard physics, time operates under fundamentally different mathematical constraints than physical space. You can move forward, backward, left, right, up or down in spatial coordinates at will. You possess complete freedom of orientation across spatial axes, but time carries an intrinsic thermodynamic arrow dictated by the second law of thermodynamics and the relentless increase of entropy. We are propelled inexorably forward through the temporal dimension at a rate governed by our velocity through space and our local gravitational potential. Now imagine what your perceptual reality would look like if your visual processing was suddenly modified to perceive time as an accessible, visible fourth dimension within the framework of a relativistic block universe. In the block universe model, past, present and future do not occur sequentially as a fleeting progression of isolated moments. Instead, all events across all epochs exist simultaneously as a static four-dimensional geometric structure. If you possessed the sensory capability to see through this temporal dimension, your perception of physical matter would undergo a profound transformation. You would no longer look across the room and see human beings as static three-dimensional figures walking across a floor. Instead, you would see living organisms as sprawling, elongated four-dimensional structures, often referred to in theoretical physics as space-time worms or world lines. Looking at a person, you would simultaneously see their entire lifespan rendered as a continuous, undulating physical tube stretching across the temporal axis. At one end of this four-dimensional structure, you would see the microscopic cluster of dividing cells inside a maternal womb. Following the continuous shape forward along the time coordinate, the tube would widen and lengthen, showing every stage of infancy, childhood, adulthood, and senescence, terminating at the moment of biological death and decomposition. Every breath, every movement, and every spatial displacement they ever made would be frozen into a singular, monumental geometric sculpture embedded permanently within the space-time block. You would not watch history happen. You would look at history as an immense, fully rendered architectural monument where the building of the ancient pyramids, the launch of modern spacecraft, and the eventual death of our sun exist as permanent, unmoving features of the universal landscape. Yet, as extraordinary as this temporal vision would be, it remains fundamentally distinct from the concept of a fourth spatial dimension. In a purely spatial four-dimensional universe, often designated as four-dimensional Euclidean space, the fourth axis, the W-axis, does not represent time, velocity, entropy, or historical progression. It is a genuine physical direction of space. It is an axis where matter can move with the exact same bidirectional freedom that we enjoy when stepping left or right, forward or backward, up or down. In this four-dimensional spatial reality, time remains an entirely separate parameter. Time would actually function as the fifth coordinate, moving the four-dimensional spatial structures forward through their own historical evolution. The mathematical distinction between a temporal fourth dimension and a spatial fourth dimension is encoded directly into the metric equations that define physical distance. In standard three-dimensional spatial geometry, the square of the distance between 2 points is calculated using the classic Pythagorean theorem, where the distance squared equals the change in x squared plus the change in y squared plus the change in z squared. If we introduce a fourth physical spatial dimension along the w-axis, the equation simply expands naturally into four-dimensional Euclidean geometry. The distance squared equals the change in x squared plus the change in y squared plus the change in z squared plus the change in w squared. All four spatial coordinates share the exact same positive sign. Every spatial axis contributes symmetrically to the overall physical distance. In sharp contrast, the space-time interval in relativistic physics utilizes a hyperbolic Minkowski metric. In this framework, the space-time interval squared equals the change in spatial coordinates squared minus the speed of light multiplied by the change in time squared. Notice the crucial negative sign attached to the temporal component. This negative sign marks the profound mathematical divide between space and time. It ensures that time behaves not as a standard spatial avenue of travel, but as a causal constraint that preserves the laws of cause and effect throughout the universe. When theoretical physicists search for hidden higher dimensions beyond our familiar three, such as in Kaluza-Klein theory, superstring theory, and 11-dimensional M theory, they are not simply relabeling time. They are investigating whether our universe contains actual, microscopic physical spatial directions that are curled up into complex geometries at the subatomic Planck scale. If you were endowed with the ability to see a fourth physical spatial dimension, you would not be looking at an individual's past or future. You would not be looking at a space-time worm spanning decades of historical movement. Instead, you would be observing that individual's physical anatomy at this exact, instantaneous present moment, but from an entirely new angle of physical reality that encompasses an extra direction of real physical space. You would see their internal cellular structures, their skeletal system, and their neural pathways precisely as they exist right now, because your line of sight would be traversing an extra physical corridor that bypasses all three-dimensional barriers. You would possess the spatial freedom to move around solid three-dimensional objects, not by waiting for them to move across time, but by physically stepping in a spatial direction that three-dimensional matter cannot navigate. Distinguishing between temporal and spatial dimensions is essential for any scientific exploration of higher dimensional reality. While relativistic spacetime reveals the profound unity of time and physical movement, the quest to visualize a fourth spatial dimension pushes the boundaries of geometry itself, asking what physical structures might exist if space itself holds more avenues of existence than our biological senses have ever been capable of registering. If your optical biology and neural processing were suddenly re-engineered to receive light traveling along a fourth spatial axis, the very concept of visual obstruction would cease to exist. To understand why this occurs, we must examine how sight actually functions across different dimensional perspectives. In our everyday three-dimensional world, your eyes do not actually capture three-dimensional space in a single glance. Your retinas are flat, two-dimensional surfaces located at the back of your eyeballs. When light reflects off an object, it projects a two-dimensional image onto your retina. Your brain then performs sophisticated geometric calculations, comparing subtle differences between the images from your left and right eyes, evaluating parallax, shadows, and relative scale, to reconstruct a mental representation of depth. Because our retinas are two-dimensional, any opaque physical surface positioned between your eyes and an object completely blocks the photons reflecting off that object. If you place your hand in front of your face, your palm absorbs and reflects the light, creating an absolute visual shield that conceals everything behind it. Now, reconsider the perspective of a two-dimensional entity residing in Flatland. To a flat creature on a plane, a solid perimeter line drawn around an object acts as an impenetrable, opaque fortress. If a square is trapped inside a closed perimeter, another flat observer standing outside cannot see inside that square. From their vantage point, the outer boundary wall fully absorbs and regrets all two-dimensional light rays moving within the plane. The interior of the square is entirely hidden from planar view. However, when you, a three-dimensional human, look down upon that very same Flatland square from above, along the vertical z-axis, the boundary walls do not obstruct your vision at all. The perimeter lines only exist within the two-dimensional plane. Your line of sight approaches the square from an entirely unblocked perpendicular angle. You can see the interior of the square, its inner geometric core, and every point enclosed within its walls with total clarity, all without punching a physical hole through its perimeter. This exact mathematical geometric relationship applies when a four-dimensional visual apparatus looks upon our three-dimensional universe. In our world, an opaque steel bank vault consists of 6 flat three-dimensional walls, a floor, a ceiling, and 4 surrounding sides. To any three-dimensional human standing anywhere in the room, those walls form a completely enclosed boundary. Every path light can travel through three-dimensional space is blocked by dense atoms of steel. Yet to an observer endowed with four-dimensional vision, that sealed bank vault is not enclosed from all directions. The 6 walls of the safe only enclose three-dimensional space along the X, Y, and Z axes. The vault is entirely open along the 4th spatial direction, the W axis. Looking at that vault with four-dimensional eyes, Your line of sight does not need to pierce the atomic structure of the steel walls. You do not require high-energy radiation such as X-rays or gamma rays to penetrate the material density. Instead, regular visual photons traveling along the unshielded W-axis can bounce off the contents inside the vault and travel directly into your four-dimensional optical receptors without ever intersecting the physical atoms of the surrounding steel enclosure. The visual consequence is extraordinary. You would gaze at the exterior of the vault, but simultaneously you would clearly observe every single item stored inside it. You would see the intricate internal mechanical tumblers of the combination lock, the stacks of paper currency, the molecular grain of the gold bars sitting on the shelves, and the structural integrity of the interior framework. The steel enclosure would no longer act as an opaque barrier. It would simply frame the internal volume within a larger spatial canvas. Now, scale this optical phenomenon up to the human body. When a physician performs an examination using conventional three-dimensional vision, they are restricted to observing the exterior surface of the skin. To analyze internal pathology, medicine relies on computational tomography, magnetic resonance imaging, or physical surgical incisions. With four-dimensional sight, the human body is completely laid bare to direct visual inspection. Because our skin, muscle tissue, and skeletal structures only form continuous boundaries in 3 dimensions, every internal biological system is fully exposed along the four-dimensional perpendicular axis. You would look at a living, breathing person and see their entire anatomy rendered in crystal-clear visual detail without causing them the slightest physical harm or discomfort. You would observe the 4 chambers of their heart contracting in real-time rhythm, the precise opening and closing of the mitral and tricuspid valves, and the hydrodynamic flow of oxygenated blood surging through the aortic arch. You would see the branching bronchial trees of the lungs expanding with each breath, the peristaltic motion of the gastrointestinal tract, and the microscopic capillary networks weaving through soft tissue. You would even be able to gaze directly into the cranial vault. You could inspect the folded architecture of the cerebral cortex, tracing the blood supply through the circle of Willis and observing the anatomical boundaries of deep brain structures such as the thalamus and the hippocampus without a single bone of the skull casting a shadow or blocking your view. This is not the blurry, translucent grayscale imagery generated by standard hospital radiography. Radiography works by firing high-energy electromagnetic waves through an object, measuring the varying rates of absorption across different tissue densities, resulting in a flattened 2-dimensional projection of overlapping shadows. 4-dimensional sight, by contrast, is a direct, fully illuminated optical perception. You see the true natural colors, reflective textures, and structural boundaries of internal matter under ambient light that has traversed the 4-dimensional corridor. Every solid object in our universe, from the concrete foundations beneath a skyscraper to the molten core churning deep inside the earth, would lose its opaque visual isolation. The 3-dimensional boundaries that define physical privacy, physical security, and anatomical concealment would be rendered entirely transparent, revealing an interconnected tapestry of internal mechanics that has been hidden in plain sight across an unperceived axis of space. Beyond the ability to look through solid matter, 4-dimensional vision introduces a far more radical optical phenomenon: omnidirectional perspective. In the everyday 3-dimensional world, your eyes are inherently constrained by the geometry of your vantage point. Whenever you hold a solid object, such as a colored Rubik's Cube, you can only perceive a fraction of its total boundary at any given split second. If you look directly at the front face, the back face is completely hidden from view. If you rotate the cube to inspect the top and right sides, the bottom and left sides disappear into the blind zone of your perspective. To assemble a complete mental picture of the entire object, you must physically rotate the object or walk around it, sequentially capturing fragments of its surface over time. To a 4-dimensional visual system, this limitation vanishes completely. Recall the fundamental lesson of lower dimensions. When a 3-dimensional observer looks down upon a 2-dimensional square lying on a table, the observer sees all 4 outer edges and the interior surface simultaneously in a single instantaneous glance. The 3-dimensional observer does not need to rotate the square, or walk around the table to confirm what color the 4 boundary lines are. Because the line of sight comes from the 3rd dimension, every single boundary point of the 2-dimensional object is equidistant to the higher dimensional viewpoint along the planar axes. When scaled up to a 4-dimensional observer inspecting a 3-dimensional object, this exact geometric principle holds true. Looking at that same Rubik's Cube with 4-dimensional eyes, you would perceive the front, the back, the top, the bottom, the left side, the right side, and every single internal mechanism linking the pieces together at the exact same moment. There are no blind spots. There is no hidden backside. The entire 3-dimensional surface area and internal volume are laid out across your expanded visual fields simultaneously. You do not need to walk around a sculpture to appreciate its full structural contour. Its entire 3-dimensional geometry is delivered to your visual apparatus in a unified, omnidirectional perceptual frame. This omnidirectional access does not simply alter passive visual observation. It completely redefines the rules of physical interaction and spatial manipulation. If you possess 4-dimensional visual perception, coupled with the ability to move matter along the 4th spatial axis, you can execute physical tasks that appear totally impossible under the standard laws of 3-dimensional physics. Consider a practical geometric thought experiment: an elastic rubber balloon that has been inflated with air, tied tightly at its nozzle, and placed on a table. Inside this sealed balloon lies a small, solid steel ball bearing. In 3-dimensional space, the elastic rubber membrane forms a continuous, closed topological barrier. The interior of the balloon is fully isolated from the exterior world. If a 3-dimensional surgeon or engineer wants to extract that steel ball bearing, there are only 2 possible options: untie the nozzle, or puncture the rubber wall with a sharp instrument, allowing the air to escape and destroying the structural integrity of the container. However, from a 4-dimensional physical perspective, that sealed balloon is not a closed boundary at all. The rubber skin encloses the air and the ball bearing strictly along the X, Y, and Z axes. The boundary offers 0 resistance along the perpendicular W axis. A 4-dimensional operator looking at the balloon sees the ball bearing resting completely exposed inside the 3-dimensional volume. To extract it, the operator does not touch the outer rubber surface, does not untie the knot, and does not pierce the membrane. Instead, they simply extend their reach along the 4th spatial dimension, grasp the steel ball bearing from the unshielded W direction, lift it clear of the 3-dimensional slice that contains the balloon, translate it slightly through the 4th dimension, and place it back down onto the table beside the balloon. To a 3-dimensional observer watching this event unfold in real time, the result looks like a violation of basic physical reality. The steel ball bearing, clearly visible inside the inflated balloon, would suddenly vanish into thin air. A fraction of a second later, it would materialize on the table surface next to the balloon. Throughout the entire extraction, the balloon would remain fully inflated, perfectly sealed, and entirely undisturbed. Now, apply this profound mechanical principle to the field of advanced medical surgery. In conventional modern medicine, even the most minimally invasive surgical operations require traversing healthy tissue. If a patient develops a deep malignant tumor nestled near the brainstem or embedded within the core of the liver, a surgeon must physically cut through layers of skin, fascia, muscle, blood vessels, and healthy organ parenchyma to reach the lesion. Even with specialized robotic instruments, the physical path to the target inevitably inflicts trauma on the surrounding biological architecture, creating risks of hemorrhage, infection, and prolonged recovery times. A 4-dimensional surgeon, guided by 4-dimensional visual acuity, would revolutionize surgical intervention. Because the human body is entirely open along the 4th spatial axis, the surgeon would not need to make a single incision on the patient's exterior skin. The surgeon could gaze directly into the deep cranial cavity, clearly isolating the exact boundary between the malignant tumor cells and the delicate neural tissue of the brainstem. Reaching in through the 4th dimension, the surgeon could grasp the tumor directly from its higher dimensional exposure, detach it cleanly from its vascular connections, and lift the entire pathological mass out of the body along the W-axis without a single surgical tool ever touching the skull, the scalp, the overlying cerebral cortex, or the protective meningeal membranes. The tumor would simply dematerialize from inside the patient's head, leaving the surrounding healthy brain matter completely intact, unscarred, and undisturbed. No bleeding, no incisions, no sutures, and zero structural disruption to the patient's three-dimensional anatomy. This remarkable capability illustrates the extraordinary power of higher dimensional mechanics. What we perceive as absolute, impenetrable physical barriers in our daily lives are merely local constraints of three-dimensional geometry. The moment you step into the perspective of the fourth dimension, closed systems become open corridors, opaque walls become clear windows, and physical manipulation transcends the boundaries of traditional space. To fully comprehend why our sensory experience is strictly confined to three spatial dimensions, we must step outside of theoretical geometry and examine the rigorous biological constraints of evolutionary neuroscience. If higher spatial dimensions mathematically exist within our universe, why did biological evolution never engineer optical receptors or neural networks capable of perceiving them? Why are our brains so thoroughly locked into rendering only length, width, and height? The answer lies in the unforgiving economics of evolutionary biology and the thermodynamic cost of information processing. The human brain is one of the most metabolically expensive organs in the animal kingdom. While it accounts for roughly 2% of an adult human's total body mass, it consumes more than 20% of the body's total metabolic energy at all times, primarily in the form of glucose and adenosine triphosphate. A massive portion of this metabolic budget is dedicated purely to sensory processing, with the visual system demanding the largest share of neural real estate. Over hundreds of millions of years of evolutionary history, natural selection did not optimize the sensory systems of organisms to perceive absolute, objective physical reality. Instead, evolution optimized sensory organs for survival and reproductive fitness within an immediate ecological niche. Every visual adaptation across biological life, from the compound eyes of insects to the binocular vision of predatory primates, evolved to solve immediate macroscopic three-dimensional problems. An early hominid on the African savanna needed to track the velocity of an approaching predator across the grasslands, calculate the spatial trajectory of a thrown spear, distinguish ripe fruit from poisonous foliage through trichromatic color vision, and navigate uneven terrestrial terrain. Because macroscopic physical matter on Earth is mechanically governed by three large spatial dimensions, three-dimensional spatial navigation was completely sufficient for survival. Develop biological mechanisms to register a fourth spatial dimension would have provided zero adaptive advantage for evading a saber-toothed cat or hunting game. More critically, the metabolic cost of building and maintaining a four-dimensional neural architecture would have been an evolutionary death sentence. Consider the staggering computational leap required to upgrade a three-dimensional visual apparatus to a four-dimensional one. In our biological visual system, light enters the cornea, passes through the pupil, is focused by the lens and strikes the retina. The retina is a two-dimensional mosaic of roughly 120 million rod cells for low-light detection and 6 million cone cells for color acuity. When photons strike the photopigment molecules inside these photoreceptors, they trigger a cascade of biochemical reactions that convert light energy into electrical action potentials. These electrical impulses travel along the optic nerve, pass through the lateral geniculate nucleus of the thalamus, and arrive at the primary visual cortex, located in the occipital lobe at the rear of the skull. The primary visual cortex, designated as area V1, contains approximately 140 million neurons, arranged in precise topographical maps that correspond directly to the visual field. Here, specialized columns of neurons perform massive parallel computational operations. They decompose the raw electrical inputs into fundamental geometric primitives: line orientations, contrast edges, spatial frequencies, and motion vectors. From area V1, the processed data flows along two massive computational pathways: the ventral stream, often called the Watt pathway, which processes object identity, color, and structural form, and the dorsal stream, the Where pathway, which calculates spatial location, motion, and motor interactions. Now, imagine attempting to scale this biological computational pipeline up by one spatial dimension. In a three-dimensional world, Your two-dimensional retina collects a planar projection of three-dimensional space, and your brain infers depth by processing the slight disparity between your two eyes. To natively capture a four-dimensional scene without losing critical spatial information, a biological organism would require a three-dimensional volumetric optical receptor, an eyeball that is not a hollow sphere with a flat sensory layer at the back, but a solid sensory matrix composed of billions of photoreceptors layered continuously throughout its entire volume. If a conventional human eye requires over 120 million photoreceptor cells to process a two-dimensional image, a volumetric three-dimensional retina capable of resolving a four-dimensional visual field would require an exponential increase in sensory receptors, scaling into hundreds of billions of individual phototransduction channels. The data throughput generated by such an optical system would be astronomical. The optic nerve would need to expand from a bundle of 1 million nerve fibers into a massive biological cable containing hundreds of millions of high-speed axons. The moment this immense deluge of sensory information hit the primary visual cortex, the neural architecture of the human brain would experience a catastrophic system failure. Our visual cortex is structurally wired to calculate geometric relationships across three axes. The cortical columns are arranged to cross-reference horizontal, vertical, and stereoscopic depth disparities. If billions of new signals arrived simultaneously from along the fourth spatial axis, the existing synaptic connections would be immediately overwhelmed. Every single point in your surrounding three-dimensional environment would suddenly present an extra axis of visual data. You would no longer see just the front surface of an object. Every internal layer, every microscopic boundary, and every reverse surface of every single item in your entire field of view would flood into your visual processing centers at the exact same millisecond. The visual cortex would attempt to process this visual deluge through its hardwired three-dimensional algorithms. The result would not be clear, godlike enlightenment. It would be instant, incapacitating sensory overload. In clinical neuroscience, when the visual processing pathways in the brain are disrupted or flooded with abnormal electrical activity, such as during severe occipital lobe epilepsy, complex visual migraines, or acute toxic encephalopathy, patients suffer from profound perceptual fragmentation. They experience visual agnosia, the inability to recognize objects, and spatial disorientation so severe they cannot determine which way is up or where their own limbs are located in space. If the human visual cortex were suddenly subjected to uncompressed four-dimensional optical data, this disorientation would occur on an unprecedented scale. The overlapping of infinite visual layers would render every object indistinguishable from the background. The brain's computational mechanisms for edge detection, depth perception, and object segmentation would completely collapse under the mathematical impossibility of fitting four mutually perpendicular coordinates into a three-dimensional neural map. The sheer metabolic demand of attempting to calculate these four-dimensional geometric matrices would trigger widespread neural excitotoxicity. Neurons would fire relentlessly, exhausting cellular energy reserves, depleting neurotransmitter pools, and plunging the individual into profound cognitive shock, acute spatial terror, and complete psychological paralysis. Human biology simply does not possess the physical hardware or the computational architecture to process native four-dimensional space. Because biological evolution locked us into three dimensions, humanity has had to find entirely different avenues to peer beyond the boundaries of our sensory prison. Where biology failed, human mathematics and computational science stepped in. Unable to directly perceive four spatial dimensions with our biological eyes, mathematicians developed rigorous analytical geometry and linear algebra. Using multivariable calculus, differential geometry, and vector spaces, we can describe four-dimensional, 10-dimensional, and infinite dimensional spaces with absolute mathematical precision, manipulating higher dimensional equations just as easily as we calculate the area of a basic triangle. In modern computing, we employ advanced algorithms and machine learning to bridge the perceptual gap. Supercomputers can construct accurate mathematical models of four-dimensional structures such as hypercubes, 600 cells, and complex higher-dimensional manifolds. By applying geometric projection techniques, similar to how a three-dimensional object casts a two-dimensional shadow onto a flat wall, Computers can rotate four-dimensional objects through their native W-axis and project their changing three-dimensional shadows onto our computer screens. Through these computational projections, human scientists can study the mechanics, rotations, and topological behaviors of four-dimensional space without overwhelming our biological neural circuitry. We do not need to rewrite our visual cortex to explore higher dimensions. We use the universal language of mathematics to comprehend worlds that our biological eyes were never built to see. While biological evolution never equipped us to perceive higher dimensions, fundamental physics suggests that extra spatial dimensions might be an absolute necessity for the universe to exist at all. In modern theoretical physics, one of the greatest enduring puzzles is the profound discrepancy in the fundamental forces of nature, known as the hierarchy problem. To understand the hierarchy problem, consider the four fundamental forces that govern all physical reality: the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. The strong nuclear force binds quarks into protons and neutrons and holds atomic nuclei together. Electromagnetism governs the interactions of charged particles, creating atoms, molecules, and chemical bonds. The weak nuclear force mediates radioactive decay. Gravity dictates the motion of planets, stars, and galaxies. When you compare the relative strengths of these interactions, an astonishing anomaly emerges. Gravity is unfathomably, inexplicably weak compared to the other three forces. To put this into perspective, the electromagnetic force is approximately 10 to the power of 36 times stronger than gravity. You demonstrate this profound imbalance every time you perform a simple, everyday action, such as picking up a small paperclip with a tiny refrigerator magnet. The gravitational pull of the entire planet Earth, an astronomical sphere weighing roughly 6 sextillion metric tons, is pulling downward on that paperclip. Yet a common magnet, no larger than a coin, easily overcomes the gravitational force of the entire planet and lifts the paperclip into the air. Why is gravity so absurdly feeble at the atomic scale? In 1998, theoretical physicists Nima Arkani Hamed, Savas Dimopoulos, and Georgi Diwali proposed a groundbreaking solution known as the ADD model of large extra dimensions. They suggested that gravity is not inherently weak at all. Rather, its true strength is diluted because it leaks into higher spatial dimensions that are completely invisible to our standard three-dimensional instruments. In this theoretical framework, the particles and forces of the standard model, electrons, quarks, photons, and gluons, are strictly confined to a three-dimensional spatial slice or membrane. When an electron interacts electromagnetically with a proton, the photons carrying that force can only propagate through our familiar three dimensions of length, width, and height. Because electromagnetic fields spread strictly within three-dimensional space, their strength falls off predictably according to the standard inverse square law. Gravity, however, is not a force mediated by particles attached to our three-dimensional membrane. In general relativity, gravity is the very curvature of space-time itself. Therefore, theoretical particles that mediate gravitational interactions, known as gravitons, are completely unconstrained by our three-dimensional boundaries. When two masses interact gravitationally, gravitons radiate outward in all available physical directions. If a fourth, fifth, or sixth spatial dimension exists, gravitons do not stay trapped within our three-dimensional slice. They freely propagate and dilute across the higher dimensional volume, bleeding gravitational energy away into the surrounding bulk of higher space. As a result, we only experience a tiny fraction of gravity's true magnitude. At microscopic distances, below the threshold where these extra dimensions are compactified, gravity becomes just as strong as the electromagnetic or strong nuclear forces. This brings us to superstring theory and M-theory, the leading mathematical frameworks attempting to unify quantum mechanics with Einstein's general relativity into a single theory of quantum gravity. When physicists attempted to formulate quantum mechanics within the framework of point-like zero-dimensional particles, their equations consistently yielded nonsensical mathematical infinities and negative probabilities. Superstring theory resolved this fatal crisis by replacing zero-dimensional point particles with vibrating one-dimensional filaments of pure energy known as strings. Just as a violin string produces different musical notes depending on its vibrational frequency, a fundamental string manifests as an electron, a quark, or a photon, depending on how it vibrates. However, when theoretical physicists solved the quantum wave equations governing vibrating strings, they encountered a profound mathematical roadblock. The mathematics of string theory refused to function in our standard 3 spatial dimensions plus 1 time dimension. The equations yielded unphysical anomalies, tachyons with imaginary mass, and broken quantum symmetries. The mathematics only balanced and produced consistent physical predictions if the universe possessed additional spatial dimensions. Superstring theory strictly requires 10 dimensions, 9 spatial dimensions and 1 time dimension, while M-theory expands this requirement to 11 dimensions. If the universe truly contains 9 or 10 physical spatial dimensions, where are they? Why do we not collide with them when walking down the street? The answer lies in the process of dimensional compactification, a mechanism first explored in the 1920s by the physicists Theodore Kaluza and Oscar Klein. Kaluza and Klein demonstrated that spatial dimensions can come in 2 distinct geometric forms, extended and macroscopic, like our 3 familiar dimensions that stretch across billions of light years, or tightly curled and compactified, rolled up into subatomic loops so microscopic that no macroscopic object can directly travel through them. Imagine a thin electrical power cable suspended between 2 utility poles across a broad valley. If you view that cable from a distance of several miles, it appears as a perfectly one-dimensional line. An observer at that distance would describe the cable as having only length. If you track the position of a hawk flying along the cable, its position can be specified with a single coordinate. However, if you zoom in with a microscope to examine the surface of that cable up close, you discover an entirely new spatial degree of freedom. An ant crawling on the cable's surface can walk forward and backward along its length, but it can also walk around the circular circumference of the cable. What appeared as a one-dimensional line from a distance is actually a 2-dimensional cylinder with a tightly rolled, compactified circular dimension. In superstring theory, the extra 6 spatial dimensions are not extended infinitely across the cosmos. Instead, at every single point in our 3-dimensional space, these 6 hidden spatial dimensions are curled up into extraordinarily intricate, multi-dimensional geometric shapes known as Calabi-Yau manifolds. These Calabi-Yau shapes are compactified at the Planck scale, roughly 10 to the power of negative 35 meters, a scale a trillion times smaller than a single atomic nucleus. If your visual system possessed the impossible resolution to see these curled-up higher dimensions, you would discover that empty vacuum is not a smooth, empty void. Every point in the air before you would blossom into an intricate geometric labyrinth of higher dimensional topologies, where vibrating strings loop and fold through the hidden corridors of higher space, generating the fundamental masses and charges that construct our physical reality. Beyond the mysteries of gravity and the microscopic topologies of string theory, higher dimensional spatial geometry offers a profound alternative framework for understanding one of the most baffling paradoxes in all of modern science: quantum entanglement. First formally identified in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen, quantum entanglement describes a physical state where 2 or more subatomic particles become deeply interconnected in their quantum properties. When 2 particles are generated in an entangled state, such as 2 photons created from the decay of an unstable parent particle, their quantum parameters, including spin orientation, polarization, and momentum, become strictly correlated. According to standard quantum mechanics, neither particle possesses a definite, predetermined value for these properties prior to observation. Instead, both particles exist in an indeterminate linear combination of all possible outcomes, described by a mathematical wave function. The paradox emerges the moment you separate these 2 entangled particles across vast physical distances. Imagine placing one entangled photon in a laboratory in New York City, and firing the second photon across the solar system to a detector on Mars. Under the standard Copenhagen interpretation of quantum mechanics, if an experimenter in New York measures the spin of the first photon and discovers it to be spin-up, the quantum wave function of the entangled system instantly collapses across the entire distance. At that exact microsecond, the second photon on Mars immediately settles into a complementary spin-down state. This instantaneous correlation occurs regardless of whether the particles are separated by a few nanometers, several astronomical units, or opposite sides of the observable universe. Einstein was deeply troubled by this phenomenon, famously dismissing it as spooky action at a distance. Under Einstein's special theory of relativity, no physical object, signal, or piece of information can travel faster than the speed of light in a vacuum. Yet quantum entanglement appears to demand that an instantaneous communicative link exists between distant points in space, seemingly defying the fundamental causal speed limit of our three-dimensional universe. Experimental physicists have verified quantum entanglement repeatedly with extraordinary precision, ruling out local hidden variables through rigorous tests of Bell's theorem. The spooky action is undeniably real, but why does the universe permit this non-local connection? To understand how a fourth spatial dimension can resolve this physical conundrum, let us return once more to the Flatland paradigm. Imagine a two-dimensional world represented by a flat sheet of paper. On this sheet of paper live two-dimensional beings who can only perceive movement across the planar surface. Now, imagine taking a single three-dimensional solid object, specifically a U-shaped piece of metal wire, like a common hairpin or staple, and lowering it from the third dimension downward toward the paper. As the two prongs of the U-shaped wire push through the surface of the paper, they intersect the two-dimensional plane at two distinct, spatially separated locations. To a two-dimensional flatlander observing the plane, what appears on their world's surface? The flatlander does not see a continuous, single three-dimensional object because the curved bridge of the wire remains suspended in the third dimension above the sheet. The flatlander only sees two isolated, separate metallic dots appearing on their table, separated by a distance of several inches. Now, imagine you take your hand in the third dimension and push the top of the U-shaped wire to the left. Down on the two-dimensional plane, both metallic dots instantly shift their positions in perfect unison. If you twist the wire from above, the two dots immediately rotate with complementary symmetry. To the two-dimensional observer watching only the surface of the paper, this behavior looks like an impossible, non-local quantum miracle. The two dots are completely separated across two-dimensional space. There is no string, no wire, no electrical wave, and no physical medium traveling across the surface between them. Yet, the instant dot A moves, dot B responds with zero time delay. The flatlander might write intricate mathematical theories about spooky communication traveling instantaneously across their planar world. But from our three-dimensional vantage point, the explanation is trivially simple. There are not two separate objects at all. The two dots are merely two cross-sectional contact points of a single, continuous, unified geometric structure that connects seamlessly through a higher spatial dimension. When we apply this dimensional logic to quantum entanglement at the subatomic scale, a startling geometric possibility emerges. In our three-dimensional universe, when we measure two entangled particles separated by millions of kilometers, we assume they are two distinct physical entities isolated from one another in empty space. We assume this because our biological eyes and physical senses are completely confined to three spatial dimensions. However, if our universe possesses a fourth spatial dimension, those two particles might not be separated at all. Along the unperceived higher dimensional W-axis, the two particles could be the physical endpoints of a single, continuous, higher dimensional quantum filament or topological structure. They appear completely separate to us because our three-dimensional space only intersects the tips of this higher dimensional object, just like the two separate prongs of the U-shaped wire intersecting the flat sheet of paper. When an experimenter interacts with particle A in a three-dimensional laboratory, they are not transmitting a signal across millions of kilometers of empty space to particle B. They are directly perturbing the local structure of a unified higher dimensional object. The wave function collapses instantly because the measurement acts upon a single continuous physical entity whose fundamental topology is fully connected through the fourth dimension. This geometric perspective aligns elegantly with cutting-edge theoretical physics, such as the ER equals EPR conjecture proposed by Juan Maldacena and Leonard Susskind. This hypothesis suggests that entangled quantum particles, EPR pairs, are fundamentally connected through microscopic spacetime bridges or higher dimensional wormholes, Einstein-Rosen bridges. In this view, non-locality is an illusion caused by our restricted sensory perspective. What appears to be distant, mysterious, and instantaneous across the vast coordinates of three-dimensional space is actually locally adjacent, continuous, and unified within the richer geometry of a multi-dimensional cosmos. When we extend our gaze from subatomic quantum scales to the vast macroscopic expanse of the cosmos, higher spatial dimensions offer a potential solution to the deepest crisis in modern astrophysics, the invisible architecture of the universe known as dark matter. For nearly a century, astronomers have known that the visible universe does not make mathematical sense under standard gravitational laws. In the 1930s, Swiss astronomer Fritz Zwicky observed the Coma galaxy cluster and calculated that the visible stars and luminous gas did not possess nearly enough mass to keep the cluster gravitationally bound. According to the laws of orbital mechanics, established by Isaac Newton and refined by Albert Einstein, the galaxies should have flown apart into deep space. In the 1970s, astronomer Vera Rubin confirmed this cosmic anomaly with conclusive data by analyzing the rotation curves of spiral galaxies. Rubin measured the orbital speeds of hydrogen gas clouds and stars located on the far outer rims of rotating galaxies. Under standard Newtonian physics, orbital speed should decrease with distance from the dense galactic center, exactly as outer planets like Neptune orbit much more slowly around the Sun than inner planets like Mercury. Instead, Rubin discovered flat rotation curves. Stars at the extreme diffuse edges of galaxies were orbiting at the exact same high velocities as stars packed closely near the core. The only mathematical way to explain this observation within standard three-dimensional gravity was to conclude that every galaxy is engulfed within an immense, invisible halo of matter that generates enormous gravitational pull, but emits, reflects, and absorbs zero electromagnetic radiation. Today, precision cosmological observations, including measurements of the cosmic microwave background and gravitational lensing maps from space telescopes, reveal a startling reality. Ordinary atomic matter, the atoms comprising all stars, planets, nebulae, and human beings, accounts for barely 5% of the total mass-energy content of the cosmos. Approximately 27% of the universe consists of this invisible, non-baryonic dark matter. The remaining 68% is dark energy, driving the accelerated expansion of spacetime. For decades, particle physicists have searched for hypothetical subatomic particles to account for dark matter, such as weakly interacting massive particles, sterile neutrinos, or axions. Yet, after running ultra-sensitive deep underground detector arrays and colliding particles at near-light speeds inside high-energy particle accelerators, not a single dark matter particle has been directly detected. This experimental silence has led a growing faction of theoretical cosmologists to propose a revolutionary alternative. Dark matter is not an elusive three-dimensional particle at all. Instead, it is the gravitational shadow of matter situated in a fourth spatial dimension. To understand how matter could exist right next to us while remaining completely invisible, we must look to the framework of brane cosmology, formulated within 11-dimensional M-theory and popularized by physicists Lisa Randall and Raman Sundram. In brane cosmology, our entire observable three-dimensional universe is not the entirety of space. Rather, it is a three-dimensional spatial membrane, frequently shortened to a three-brane, floating within a higher dimensional spatial hyperspace known as the bulk. Imagine a two-dimensional sheet of plastic wrap suspended inside a large three-dimensional room. A colony of flat, two-dimensional microbes lives exclusively on that sheet of plastic. The particles that construct the microbes and their immediate environment, electrons, quarks, and the gauge bosons that carry the electromagnetic, weak, and strong nuclear forces, are physically anchored to the sheet. In the language of string theory, these ordinary matter particles and force carriers are open strings whose endpoints are strictly attached to the membrane. Because photons, the quantum carriers of light, are open strings trapped on the sheet. Light can only travel across the length and width of the plastic wrap. Light cannot shine outward into the three-dimensional room, nor can light from the room reach the microbes. The microbes are fundamentally blind to the third dimension above and below them. Now, imagine placing a heavy, solid, iron bowling ball on a wooden pedestal hovering just a fraction of an inch above the plastic sheet, completely detached from it. Because the iron ball exists in the third dimension off the membrane, the flat microbes on the sheet cannot see it. Photons moving across their plastic world never strike the iron ball, and light from the iron ball never enters their planar eyes. Electromagnetically, the iron ball is completely invisible and non-existent to them. However, recall the unique behavior of gravity across dimensions. In string theory, gravitons are closed strings, continuous, unbroken loops of energy with no loose ends to attach to any membrane. Because gravitons are closed strings, they are completely unconstrained by the plastic sheet. Gravitational waves and gravitational fields propagate freely throughout the entire higher dimensional bulk, penetrating effortlessly through the ambient space and passing directly into the membrane. When the heavy iron ball rests just above the plastic sheet, its powerful gravitational field reaches down through the third dimension and bends the surface of the plastic wrap. Down on the sheet, the flat microbes suddenly observe their world warping. If they roll small marbles across their flat surface near that region, the paths of the marbles will curve sharply, deflected by a powerful gravitational well. If they calculate the orbital trajectories of objects around that zone, their mathematical equations will dictate that a massive physical entity is present. Yet, when they point their optical instruments at that exact spot, their detectors register absolute vacuum. There are no atoms, no heat signatures, and no light rays. The microbes would classify this mysterious phenomenon as dark matter. They would spend generations searching for invisible flat particles on their sheet, completely unaware that the source of the gravitational pull is an ordinary three-dimensional physical mass resting right beside them, across a direction they cannot perceive. Now, scale this exact geometric model up to our three-dimensional universe, floating inside a four-dimensional spatial bulk. Under brane cosmology, our universe is a three-brane, and the particles composing our bodies, our stars, and our planets are open strings anchored to this three-dimensional slice. All photons that we use to observe the cosmos are trapped within our membrane. Meanwhile, just a sub-millimeter away along the fourth spatial W-axis, another three-dimensional brane could be floating parallel to ours within the bulk. Or, the bulk itself could contain massive four-dimensional celestial structures, higher dimensional stars, colossal hyperclusters, or dense macroscopic matter fields. We cannot see these higher dimensional structures with optical telescopes, radio dishes, or infrared sensors because photons cannot jump the gap across the fourth spatial dimension. To our electromagnetic sensors, the bulk is pitch black and undetectable. Yet, because gravitons are closed loops that roam freely through the four-dimensional bulk, the immense gravitational fields of these higher dimensional structures bleed directly into our three-dimensional universe. When astrophysicists map the gravitational lensing of light travelling past distant galaxy clusters, observing how spacetime is bent around invisible halos, we might not be looking at clouds of exotic subatomic particles scattered throughout our space. We might be looking directly at the gravitational imprint, the higher dimensional shadow, of massive physical matter that exists directly adjacent to our universe along the fourth spatial dimension. If you were suddenly endowed with four-dimensional vision, the dark cosmos would instantly erupt into breathtaking visual complexity. The vast black voids between the stars would no longer appear as empty, desolate stretches of vacuum. You would look past our three-dimensional membrane and see the monumental architecture of the bulk. Sprawling higher dimensional galaxies, colossal sheets of parallel branes, and cosmic energy filaments intersecting the fabric of reality. What we have spent centuries calling dark matter would be revealed not as an invisible mystery, but as the ordinary, tangible matter of a grander, multidimensional universe, casting its gravitational weight across the dimensional divide. Throughout human history, Our perception of the cosmos has been shaped and constrained by the biological architecture of our sensory organs. For millions of years, survival demanded that we master the three macroscopic dimensions of length, width, and height. Our eyes evolved to capture two-dimensional planar projections. Our visual cortex learned to reconstruct three-dimensional depth, and our intuition built an understanding of physics grounded entirely in solid barriers, opaque walls, and isolated objects. Yet, as we have journeyed from the geometric thought experiments of Flatland to the subatomic landscapes of superstring theory, and outward to the cosmic expanses of brane cosmology, a profound truth becomes undeniable. Our three-dimensional reality is not the absolute boundary of existence. It is merely a single cross-sectional slice of a far grander multi-dimensional reality. If we were endowed with the ability to see the fourth dimension, the universe would completely rewrite its rules before our eyes. The opaque structures that define physical isolation would dissolve into total transparency. Closed systems would become open corridors, medical surgery could occur without a single physical incision, and the perplexing non-locality of quantum entanglement would reveal itself as the natural geometry of continuous higher dimensional objects. Even the deepest cosmological enigma of our time, the invisible scaffolding of dark matter, might simply be the gravitational weight of matter residing right beside us across an unperceived spatial axis. Our biological hardware may never physically evolve to process the four-dimensional visual field without succumbing to catastrophic neural overload, but humanity possesses something far more powerful than biological eyes alone: the universal language of mathematics and theoretical physics. Through linear algebra, multivariable calculus, differential geometry, and advanced quantum field theories, human consciousness has broken free from the biological prison of three dimensions. We can map the rotations of hypercubes, calculate the topologies of 10-dimensional manifolds, and model the gravitational mechanics of the higher dimensional bulk with absolute mathematical precision. Mathematics serves as our artificial higher dimensional sensory organ, allowing us to perceive truths that lie completely beyond the reach of human sight. We are three-dimensional beings inhabiting a vast geometric canvas, continuously using the power of reason to decode the hidden architecture of the cosmos. Thank you for exploring the fourth dimension with us. Until next time, keep looking beyond the surface of reality.